You know, every single sensor in your life, the one in your phone, your car, your thermostat, it's constantly telling a story about the world around it. But what you don't see is the secret drama, the tiny race against time that happens in just milliseconds. Today, we're pulling back the curtain on the secret life of a signal.
I mean, really think about that for a second. You stick a digital thermometer under your tongue. Your temperature changes for the thermometer instantly, right? But that little number on the screen, it has to climb and climb and climb before it finally beeps. Why is that? Well, it's because sensors aren't magic. They're physical things, and they have to race to catch up with reality. And that race, that's what we're breaking down right now.
Okay, so let's actually follow a signal on its journey. We're going to put it on the clock. We'll start right from the beginning. That moment the physical world changes, and we'll follow it all the way to the finish line, when it finally gives us a stable, trustworthy number. This whole race is governed by what engineers call a sensor's dynamic characteristics. At the end of the day, this is the real challenge, right? Something happens, and the sensor's job is to translate that event into data we can use. But that translation, it's not instant. The sensor has to feel the change, react to it, process it, and then spit out a signal. That whole chain of events takes time, and how it all unfolds determines if the story it's telling is actually true. So, boom, a change happens. The starting gun has fired. The very first thing we want to know is, how fast is this sensor? How quickly does it bolt off the starting line? This initial burst of speed is absolutely crucial, and it turns out there are a few different ways we measure it.
The first major checkpoint in this race is called response time. And notice the key phrase there, a large percentage of the final value. We're not talking about the time it takes to get to 100%. It's more of a practical measure of when is this signal good enough to actually use.
So why 95%? Why not 100? Well, it's all about physics. See, as a signal gets really close to its final true value, it usually slows way down. That last little bit can take forever. Think of a curve that gets flatter and flatter as it reaches the top. So for most things, hitting 95% is close enough, and it gives us a much more reliable way to compare the real-world speed of different sensors. Now, if you want to get a little more technical, engineers use something called the time constant. This is the time it takes to get to a very specific number, 63.2% of the final value. And I know, that number sounds totally random, right? But it actually comes directly from the core math that describes how a lot of things change in the real world. It's like a universal yardstick for a sensor's raw quickness. And then there's one more, rise time. This one is cool because it ignores the slow start and the slow finish. It just focuses on the main event, that steep, fast climb in the middle, usually from about 10% up to 90%. You can think of it as measuring the sensor's absolute top speed while it's in the thick of the race. So our signal is moving fast, it's climbing, but what happens when it has a little too much momentum? Sometimes, in its rush to tell us the new story, a signal can blow right past the correct value. And this is where things get really interesting. And this just perfectly shows the difference between a perfect world and our world. Ideally, a sensor would just climb to the true value and stop perfectly on a dime. But in reality, it often has overshoot. It soars right past the target. Then it has to correct itself, maybe bouncing up and down a little bit before it finally finds its new home. And the time it takes for all that bouncing to calm down, we call that the settling time. All right, the race to respond is over. The drama has settled down. Now we have to ask the biggest question of all. Was the story the sensor told us actually true? Because speed is one thing, but accuracy? Well, that's everything. This brings us to this really great concept called fidelity. A sensor with high fidelity doesn't just get the final answer right. No, it accurately shows us how the change happened. If the temperature went up slowly, the high-fidelity sensor shows a slow, smooth climb. It tells the story of what actually happened, without twisting the facts. The flip side of fidelity really is something called dynamic error. This is basically the gap between what's really happening and what the sensor is telling us while things are changing. So during that rise time, that overshoot, that settling time, any moment when the sensor's reading doesn't quite match reality, that's dynamic error. Now, I know what you might be thinking. This all sounds pretty deep in the weeds, super technical, but understanding the secret life of a signal is so important because out in the real world, a few milliseconds, a few percentage points of overshoot, that can have massive consequences. Just think about the stakes. For a self-driving car, a slow response time on a sensor could be the difference between a smooth stop and an accident.
In a hospital, a heart rate monitor that overshoots could trigger a false alarm and cause total panic. Or in a plane, a flight control sensor that has poor fidelity, one that lies about the plane's true position, could be catastrophic. In these systems, speed and accuracy aren't just numbers on a spec sheet, they're literally life and death.
So here's the bottom line, the crucial point to all of this. Designing a sensor is all about a balancing act. You can make a sensor that is unbelievably fast, but it might overshoot like crazy. Or you can make one that's perfectly stable and accurate, but it might be way too slow to be useful. The real art is finding that perfect trade-off between speed and accuracy for the job it needs to do.
And that kind of leaves us with one last big question. As we build faster cars, smarter AI, and systems that react in the blink of an eye, our demand for instant, perfect data is just exploding. That secret race against time happening inside every sensor is more critical than ever. So are we actually building sensors that are fast enough and true enough to keep up with the world we're creating?